Alright, in this video, we will be discussing 3 integration techniques using AB and BC calculus. These include improper integrals, trig substitution, and partial fractions. First, we will start with improper integrals. Improper integrals occur when we are not allowed to take the integral due to the limits of integration. Instead, we use limits in order to take the integral. The first case is when one of the limits of integration or both limits of integration are either negative infinity or infinity. In order to correct this, we use a constant b. Instead of taking the integral from a to infinity, we will take the integral from a to b and take the limit as b approaches infinity. This serves the same purpose. As you can see, we will be taking this integral, which is the same because b will approach infinity and it will take this area. This might also be reversed, and the bottom limit of integration might be negative infinity. We could do the same thing to correct this. We could set the limit as a approaches negative infinity and take the integral from a to b. This will be this area right here. But when we have to take the integral from negative infinity to infinity, it gets a little more complicated. We would have to split the integral from negative infinity to a constant c and c to infinity. As you can see, these two areas will be equal to this area. The first area is represented right here, and the second area is represented right here. But because we have negative infinity and infinity in these integrals, we will have to use the first two definitions of integrals in order to solve this. From negative infinity to c, we will use this definition. From c to infinity, we will use this definition. In the practice problems, we will demonstrate this rule. Right now, we will be practicing these 3 techniques of trying to solve improper integrals, and then we will discuss the different cases. So we're going to take the integral from negative infinity to 1 of the function 1 over x to the 5th. So we can't have negative infinity as one of the limits of integration, so we'll take the limit as a approaches negative infinity of the integral a to 1 of the function. Now we integrate as usual, so negative 1 over x to the 4th, 4x to the 4th, from a to 1, limit as a approaches negative infinity. So if we replace 1 into the function, we get negative 1 over 4. And then if we replace a, it approaches negative infinity, so the negative 1 becomes insignificant. So it becomes minus 0. So the answer to this problem is negative 1/4. Done. Okay, so this problem is going to be a little more complicated because it involves integration by parts. If you haven't learned this yet, check out the other video and then you'll be able to do this problem. So we're going to take the integral from 0 to infinity of 1 plus 2x times e to the negative x. So again, we can't take the integral because infinity is one of the limits of integration. So we take the limit as t approaches infinity, the integral 0 to t, 1 plus 2x e to the negative x. Now we'll be doing integration by parts. So the basic formula for integration by parts is u dv equals uv minus the integral v du. So in this case, u is 1 plus 2x. So du will be 2 dx. Now dv is e to the negative x. So v is equal to negative e to the negative x. And then you use this formula to transform this equation. So negative 1 plus 2x e to the negative x plus 2 e to the negative x dx. Then we integrate this expression. And we always have to have the plus c because this is an indefinite integral. Then we simplify, negative 2, negative 1, so 3 plus 2x times e to the negative x plus c. So now that we have that, we could go back to this and use the limit as t approaches infinity of the integral 0 to t of this expression. So instead of evaluating this integral with a negative, we could switch these two and then get rid of the negative. So the limit as t approaches infinity of 3 plus 2x times e to the negative x evaluated 0 and t. So when we replace 0, this becomes 0 and this becomes 1, so you have 3 left. So it's 3 minus the limit as t approaches infinity, and then we'll replace t into this. 3 plus 2t. And because e to the negative x is pretty much e to the x in the denominator, we could put it into the denominator. There. So the 3 here is insignificant because 2t and e to the t. And e to the t grows faster than 2t when it approaches infinity. So this whole expression becomes 0. So the answer is 3. So this integral converges because it becomes one single value. Okay, so this problem gets a little more complicated because it has negative infinity and infinity as the limits of integration. So this is the problem. The integral from negative infinity to infinity of 6x to the third over x to the fourth plus 1 squared. So we have to split this up into two integrals, negative infinity to some constant and the constant to infinity. The easiest constant that I could think of right now is 0, so let's just choose 0. So negative infinity to 0, 6x to the third over the fourth plus 1 squared plus 0 to infinity, 6x to the third over x to the fourth plus 1 squared. Again, we can't have negative infinity or infinity as any of the limits of integration, so we'll use limits. The limit as a approaches negative infinity, so we'll place a right over here, a to 0, 6x to the third over x to the fourth plus 1 squared. And then again, we'll use a different variable here, so as b approaches infinity. So where the heck? The limit as b approaches infinity, 0 to b, 6x to the third over x to the fourth plus 1 squared. Okay, so we're going to use u substitution to find this integral. So we'll set u equal to x to the fourth plus 1. Du is equal to 4x to the third dx. And then we replace it back into the integral, so integral 6x to the third dx is equal to du divided by 4x to the third. So du divided by 4x to the third, and we have u squared right over here. So this cancels out, 2, 3, these cancel out. So we're left with the integral of 1 over u squared du. And we have 3 over 2, so we could pull that constant out. So this is our integral. Okay, so I erase some things to make more space on the board. So this integral becomes 3 halves of negative 1 over u. And then we could replace u back into it, so it becomes 3 halves. We use this value of u, negative 1 over x to the 4th plus 1. Okay, so let's erase this to make some space. So what we have now is the limit as a approaches negative infinity of negative 3 over 2 times 1 over x to the 4th plus 1 evaluated from a to 0 plus the limit as b approaches infinity of the same expression x to the 4th plus 1 evaluated from 0 to b. Okay, so when we replace 0 into here, we get 1 over 1 times negative 3 over 2. So we'll end with negative 3 over 2. And then when we put a, which is approaching negative infinity, into here, the 1 becomes insignificant, this becomes insignificant, and it becomes practically 0. So we'll have nothing here. Now, when we replace b into this, the same exact thing happens because b is approaching infinity. So the negative 3 halves and the 1, they all become insignificant, and it becomes pretty much 0. And then when we put 0 into this expression, it's 1 over 1 times negative 3 halves. And because it's minus negative 3 halves, it becomes plus 3 halves. So this value becomes 0. So this integral is convergent. The second case is shown in the magenta here, and it happens when there's an infinite discontinuity. As you can see in these graphs, there are discontinuities at A, B, and C. So there are 3 conditions for this rule as well. So, in the first case, if f of x is continuous on the interval from a to b inclusive, a not inclusive, as you can see, then the integral from a to b of the function is equal to the limit as c approaches the right-sided limit of a from c to b of the function. So, we are trying to take this area, we are trying to find this area, and a does not actually exist. It could be negative infinity or infinity if you take the left or right-sided limit, but the actual value of a does not exist, so we can't take the integral. In order to remedy this, we set c to be a, but c cannot actually equal a. C has to be equal to a approached from the right side, because we are trying to take this area. The second case is if the function is continuous on the interval from a to b, here to here, a inclusive, b not inclusive, because again, it does not exist. Then we will do the same exact thing, but with the left-handed limit of b. By taking the left-handed limit, we are able to take this area without actually using the value b. Similar to the third example shown here, the third example here gets a little more complicated. If we're trying to take the area from a to b, we will have to split it up to the area from a to c and the area from c to b. Again, we cannot take the integral from a to c because c is an infinite discontinuity. So instead of taking the area from a to c, we will be taking the area from a to c of the function as another constant approaches c from the left-hand side, so the left-handed limit. We will have to do the same from c to b, so c to b correlates to the first definition. Now we will do some practice problems to practice how to take integrals with infinite discontinuities. Okay, so the next case that we learned about is when there's an infinite discontinuity in the function. So let's start with a pretty simple example. Integral from 0 to 4 of 1 over x squared. So if we were to try to put in 0, it would not exist, so we have to set a limit. So instead of this, we do the limit as c approaches 0 from the right side. We do it from the right side because we're taking the integral from 0 to 4. So on the graph, it would have to be approached from the right side of c to 4 of 1 over x squared. So when we evaluate this, the integral becomes this, and we're evaluating this c to 4, the limit as c is approaching 0 on the positive side. So when we plug in 4, we get negative 1/4. And then when we plug in c, we get plus 1 over c. The limit c is approaching 0 from the right side. So when we do this, we get 1 over a value that's very, very, very small. So if we do 1 over a value that's very small, we get infinity. So negative 1/4 becomes insignificant, and we end with infinity. So this integral is divergent. Done. So the last problem we did had a limit as c approaches 0 from the right side, so now we're going to do the limit as c approaches 4 from the left side to show the different perspective. So the problem is the integral from 0 to 4 of 1 over square root of 4 minus x. So if you try to put in 4, you would get 0 in the denominator. Again, this does not exist, so we set the limit. The limit as c approaches 4 from the left-hand side. We do left-hand side because we're taking the integral from 0 to 4. So what would be included in this integral would be 4 from the left-hand side, not the right-hand side. So we do that. Integral 0 to c of 1 over 4 minus x dx. And then we evaluate this integral. This integral becomes negative 2, 4 minus x to the 1/2. And we're evaluating from 0 to c, the limit as c approaches 4 from the left-hand side. Okay, so we'll put in c, negative 2, 4 minus c to the 1/2, the limit as c approaches 4 from the left-hand side. And then when we put in 0, we get 4 to the 1/2, so root 4, which is 2. And then root 4, 2 times negative 2 is equal to negative 4, but we're doing minus that, so we get plus 4. So when we evaluate this limit, it's approaching 4 from the left-hand side. So what we would get is if you put in 4, it'll be practically 0, and 0 times anything is 0. So we'll get 0 plus 4. So the answer is 4. This integral is convergent. But this problem gets a little more complicated because we're going to need to use 2 integrals to solve it. This is because there is an infinite discontinuity within the integral. It's not one of the limits of integration. So let's start. The problem is from negative 1 to 1 of e to the x over e to the x minus 1. So we'll set it to 2 integrals because at 0 there's an infinite discontinuity. Integral from negative 1 to c. We'll do the limit as c approaches 0 from the left-hand side because that would be in the integral of e to the x over e to the x minus 1 dx plus the limit as d approaches 0 from the right hand side, integral d to 1 of e to the x over e to the x minus 1 dx. So we're going to use u substitution to find the integral. U is equal to e to the x minus 1, so du is equal to e to the x dx. So if we replace this all back in, you get the integral of 1 over u du. Okay, so when we take this integral is ln of u, and we know that u is e to the x minus 1, so ln of the absolute value of e to the x minus 1. And we're going to evaluate this from -1 to c, the limit as c approaches 0 from the left-hand side for the first part. So when we do this, we first plug in c, so we get the limit as c approaches 0 from the left-hand side of ln of e to the c minus 1 minus ln of e to the -1 minus 1. So we're going to use the graph of e to the x to try to solve this. So the graph of e to the x looks like this. Y equals e to the x. So if it's approaching 0 from the left-hand side, e to the 0 we know is 1, and it decreases as it goes to the left. So if it's approaching 0 from the left-hand side, it'll be a little bit less than 1. So we could just plug in a value just to make it a little bit simpler. Minus 1. So after that, we have to look at the graph of ln of x. The graph of ln of x looks like this. Y equals ln of x. So this is going to be a very, very small positive value because we're taking the absolute value. So this positive value we could just pretend is 0.01. Ln of 0.01. As you could see, 0.01, that would be, the value would be -infinity. So this is -infinity. We could plug this into a calculator, but it's not really necessary because we already know that this function is divergent. So what we did in this problem is just the first part. The second part we don't have to do now because we already know that the first part is divergent, so the second part doesn't really matter. So the answer to this problem is just divergent. Partial fraction decomposition is a method used to integrate rational fractions. In this method, we write the rational function as a sum of basic fractions or partial fractions, and then we integrate the rational function by integrating the sum of partial fractions. First, we will start with the method if the fraction is proper. This means that the degree of the numerator is less than the degree of the denominator. You write out the factors of the denominator, the linear and quadratic factors. So if a quadratic factor cannot be factored more into linear factors, we will just keep it as a quadratic. So in this case, there's one quadratic factor, a double linear factor, and a single linear factor. Then we set up the partial fraction decomposition. We put one single variable over each linear factor, a, b, c, and then we put dx plus e, or a linear expression, over the quadratic factor. Also, if there's double of any factor, such as x minus r, you keep x minus r to the first power, and you also put x minus r to the second power as another denominator. But even though this multiplies out to be quadratic, you keep the numerator one single variable, similar to these linear factors. Then you will multiply by g of x on both sides to clear all the denominators. Then you will get an equation like this. In this problem, it would be a little difficult to multiply this out, but in an actual problem, it would be easier. So you would multiply it out, and then you would put all the x to the fourth terms together, x to the third terms together, all the way down to the constant. Afterwards, you would factor out the x to the fourth, so there would be this red expression. This red expression has to correlate to this expression. So by doing this, you would end up with 5 equations. The red, light green, dark green, brown, and purple. Now you could solve these expressions by a system of equations or a matrix, and then you will get the variables a, b, c, d, and e. This might not make too much sense right now, but in the practice problems you will be able to fully understand this concept. Then you replace the values you obtain for these variables into the original equation, right over here or right over here, and then you integrate. Remember to have the dx's when you're integrating, or you might get points off for the problem. So when you integrate, a is a constant, b is a constant, c is a constant. So these constants go out, and then you will use the natural log of the absolute value of the denominator for the bottom. The third integral, you won't have to use the natural log because it's a linear factor squared, so it will just end up being the linear factor to the negative first power multiplied by c. The fourth integral we wouldn't be able to solve for right now, so you would use substitution or some other method learned in another video to integrate. And you must not forget the plus c because this is an indefinite integral, so you must always have the plus c. Now, the method for an improper integral, it's pretty much you divide to get a polynomial plus the proper fraction, and then you use partial fraction decomposition shown here for the proper fraction, and the polynomial you just integrate normally. Now we will be doing some practice problems to demonstrate how partial fraction decomposition works. Let's start with a basic partial fraction decomposition problem. We're going to try to integrate 6x plus 7 over x plus 2 squared. So because the factors are x plus 2 and x plus 2, we will have x plus 2 as one of the denominators and x plus 2 quantity squared as the other denominator. So this will be equal to a over x plus 2 plus b over x plus 2 squared. Even though this would technically be a quadratic factor and this would have to be linear, we keep this as one constant because it's x plus 2 squared. So then we multiply by the denominator x plus 2 quantity squared, so we get 6x plus 7 equals a times x plus 2 plus b. Then we multiply out, and then we group by terms, so ax plus 2a plus b is the constant, 6x and 7 is a constant. Now we're going to set up a system of equations. 6 equals a here and here, 7 equals 2a plus b. If we replace 6 into this equation, we get b equals negative 5. Okay, so we're going to replace a and b back to here, so let me erase all this. A is 6, b is negative 5, 6, negative 5. So we're trying to find this integral, so we could make all these integrals. Now we could take out 6 because it's a constant, so it'll be 6 ln of the absolute value of x plus 2. And then because it's x plus 2 squared and negative 5 is a constant, we could take out negative 5, it'll be negative 5, and then it'll be x plus 2 to the negative 1. So the integral of this is equal to 6 ln of the quantity x plus 2 plus 5 x plus 2 to the negative 1. And then we also have to put the plus c because it's an indefinite integral. Okay, so in this problem we're going to be integrating 3 minus x over x times x squared plus 1. So this problem will be a little more complicated because one of the factors in the denominator is quadratic. So when we set this up as a partial fraction decomposition, we're going to have it equal to a over x, because this is a linear factor, this will only be one variable, plus bx plus c over x squared plus 1. Because this is quadratic, this has to be linear. So now we multiply to get rid of the denominator. And we multiply this out. And then we're going to group the like terms together. So a plus b squared plus cx plus a equals 3 minus x. So here we have 0 as the coefficient for x squared. So a plus b is equal to 0. Then the coefficient of x is negative 1 here, so negative 1 is equal to c, and the coefficient of the constant a is equal to 3. And if we put 3 into here, we know that b is equal to negative 3. So we have the values for a, b, and c, so we could erase all this. A is equal to 3. B is equal to negative 3, and C is equal to negative 1. So now we integrate. So integral of 3 minus x over x times squared plus 1 is equal to the integral of 3 over x minus the integral of 3x over x squared plus 1, and then we're going to separate these two, so it'll be minus the integral 1 over x squared plus 1. So this integral is pretty easy to take. It's just going to be 3 ln of x, and this integral is going to be a little harder. We're going to have to use u substitution, so u is equal to x squared plus 1 du equals 2x dx, and then by that we know that this will end up being 3 halves ln of x squared plus 1. And then the last one, if you know your trig identities for integrals, you'll know that it's inverse tan. So it'll be minus tan inverse of x. And we always have to add the plus c because it is an indefinite integral. So the integral of this is equal to this. Trig substitution is something that is more easily learned by practice, but I will be showing you the basic method right here. It is used to replace binomials of the form a squared plus x squared, a squared minus x squared, or x squared minus a squared. So if you see these in the integral that you're trying to take, then use trig substitution. The basic idea behind trig substitution is first you set up a triangle, and then you use this triangle to replace the things inside the integral in terms of theta. You might want to memorize these 3 triangles because they'd be helpful in the problems. If you have a squared plus x squared, you put it on the hypotenuse. If you have a squared minus x squared, you put it on the horizontal line. And if you have x squared minus a squared, you put it on the vertical line. So this is the method used in trig substitution. First, you replace the binomial with a trig expression. We'll show this in the practice problems. And then you replace the dx with an expression involving d theta. So you try to replace all the x's with thetas. After you integrate the expression with the function in terms of theta, and then using the triangle and substitution, you replace all the thetas in the expression that you get with x's. And you always have to remember the plus c if it's an indefinite integral. Now we will do some practice problems to evaluate some integrals in which we will use trig substitution. Okay, so the first trig substitution problem is pretty simple. We're going to take the integral of 1 over root 9 minus x squared. So as I showed before, this would mimic, it takes the form of a squared minus x squared. So our triangle will look like this. A squared minus x squared would be right over here, 9 minus x squared. Then a is 3, and then x is right over there. So we know that sine of theta is equal to x over 3. So we could multiply both sides by 3, so 3 sine theta is equal to x. And then we could find the derivative of both sides. 3 cosine theta d theta equals dx. So with this, we can replace the dx right over here, and we could convert it to theta. Then we also have to convert this expression to theta. So we know that cosine of theta is equal to root 9 minus x squared over 3. Multiply both sides by 3. Cosine of theta is equal to root 9 minus x squared. So we can now replace this expression involving x with the expression involving theta. So when we replace everything, we get this value right here, 3 cosine of theta d theta over 3 cosine of theta, the integral of that. These cross out very conveniently, and then we end with theta as the evaluated expression. So in order to get theta into terms of x, we know that the inverse sine of x over 3 is equal to theta, so the answer is sine inverse of x over 3. Again, we can't forget the plus c because this is an indefinite integral. So that is the answer. Okay, so this trig substitution problem is a little more complicated. We're going to take the integral 1 over x squared minus 4 to the 3 halves dx. So this mimics x squared minus a squared. So the triangle will look like this. Squared minus 4, then we'll have 2 right over here, and then x right over here. This will be theta. So we know that secant of theta is equal to x over 2, and then we can multiply both sides by 2, and then we can take the derivative of both sides. So now we have the replacement for dx into terms of theta. Then we have to replace this expression right here. So we know that tan of theta is equal to root x squared minus 4 over 2. Multiply both sides by 2. And now we could replace everything back to this to simplify the expression. So right over here, d theta 2 tan of theta secant of theta over 2 tan of theta to the third. I'm going to try to find that integral. So this simplifies to the integral of cosine of theta over 4 sine squared of theta d theta. So let me erase a little bit to have more space. I'll write this up here. Cosine of theta over 4 sine squared of 2 theta d theta. Then we could use u substitution to solve this. U will be equal to sine of theta. Du is equal to cosine of theta d theta. So this will all cancel out and become 1/4 integral 1 over u squared du. That becomes negative 1 over 4u. And u is sine of theta, so negative 1 over 4 sine of theta. Now sine of theta we could get from this triangle, so we get negative 1/4 times 1 over root x squared minus 4 over x. This will end up being negative x over 4 root x squared minus 4. And then we always have to remember the plus c, indefinite integral plus c.